Hi everyone, I'm William. Today I'm presenting my final deliverable. It's a Bayesian model optimization, um, the single level model and multi-level model comparison. The motivation for this project is to explore performance when working with Bayesian models, to observe the time that's spent on training with both models with football match dataset. And then we draw the conclusion about the pros and cons of both models. Here's the experiment data set here, which is that's what we targeted to do model efficiencies tests. And this very small data set, only 300, about 300 entries. Um, we're going to use a single level model and multi-level model to test this data set. Um, let's discuss the multi-level model first. So the learning strategy about this multi-level model, what hyperparameters does this multi-level model has, and how is do the score rate modeling on this model. The model learning strategy is basically 5 key points. So it's learning individually and globally, which means the model is learning the each team from the data set, and also learning across the league uh, of, of all teams. Um, this, which means while it's learning its defense power, attack power, it also draw this defense and attack to um, learn from the whole across the league, all the matches, to make the best estimate. So each team has a separate attack and defense abilities pull around league-wide average. Um, and then this model uses home advantage as the additional condition. This is a single parameters that captures the systematic effect of playing at home. Um, this model also normalizes the score using offset um, by subtracting that values um, with the total value of the global average, which is the mean of attack power and defense power across the league. That will preventing the model from inflating or deflating goal counts across all matches. So also the partial pooling is the placing normal power areas on each team's attack and defense parameters, so that can avoid overfitting to ensure that teams with fewer matches are strung toward to the global mean, to avoid extremely uh, distributed value on the normal distribution. Um, let's go a little bit deeper on the hyperparameters. Um, so the hyperparameters from this model has global parameters and the team specific parameters. Um, so we have the normal distribution of attack power and the normal distribution of defense power. Attack power and the variance of both with explanation values. And also we added the home advantage for the global parameters. Um, and then team specific parameters, it's every team has its own attack ratings and defense rating. Since these parameters are drawn from normal distribution with the league level means and variance, um, the model partially proves teams' rating toward to the global average to reduce the overfitting. For the score modeling, the likelihood of this model is using the home advantage plus the specific team's attack power and defense power to minus the offset to normalize the score. Um, but yeah, so otherwise, away team will not adding the home advantage, but still normalize their both strengths of attack power and defense power. Um, and putting everything together, the posterior is the probability of distribution that represent our updated belief that team strength after seeing match data. Um, so also here shows the posterior's formula. This is the posterior is the proportion of the probability of score that says specific score given by the attack and the defense power and the home advantage of the team times the attack power of the variance and mean of the attack power by the global parameter and the defense of given mean of global parameters of defense power and variance of defense power times each individual's probability of normal distribution of attack power, defense power, variance of attack power, defense power with probability of a home, the team that is the home has the home advantage. So besides observing the data, the team attack and defense follow the board distribution, which is a global across the league. So after observe the data, this distribution will sync toward a realistic value based on match outcomes. And how is sampling is using the MCMC sampling, which computes the posterior by drawing thousands of samples. The pros of this model is better generalization to new or low data teams, which some teams have really low match data. Probably across the league, there's a team only have few matches. This model is good at analyze those low data teams from the league-wide distribution. So we can borrow the information from the across the league distribution to give a good estimate for the team that low data teams attack and defense power, and also helps for overfitting to small sample size. Also captures uncertainty better, provides not just a point estimate but a distribution over each team's attack and defense, more useful when considering confidence in predictions. This model is more flexible, can additionally adapt and some factors as players' injuries, home advantage variations, and tactical changes. Cons about this model. So requires sampling methods that takes longer to converge. And computationally expensive compared to Poisson regression, the single level model, because it captures more uncertainties and adaptable to new conditions. Requires sampling team parameters, hyperparameters, and slower MCMC mixing because of correlated parameters. Inference is nonlinear. The running time of this model is O of n squared. And it's more difficult to interpret because attack and defense are hierarchy model. Individual teams values depends on league-wide trends. Um, Harder to explain compared to direct estimate from the single level. Compared to the single level model, it's harder to explain because the more complicated condition that adapted. Uh, and also, it's really time consuming when you analyze the small data set, which is it takes way longer than the single level model. Um, and then let's talk about a single level model and let's talk about how it works. Same thing, talk about the hyperparameters and how the score remodeling looks like. So the learning process of this model is first is to initialize priorities for attack, defense, and home advantage. If applicable, and applied to this model. Um, Individual teams attack power, individual defense attack power will be using a fixed normal distribution with the mean value as 0 with 0.2 variations. The estimate parameters by maximizing this likelihood is pretty much we are just adding the global normal distribution with the home advantage, and then we uh, capture the fetch the attack power, defense power from the specific team, add them together and get a score. This formula shows that if the higher the score, higher attack score means more goal score, and higher defense, fewer goals to achieve. And we using lambda for the exponential values. And we're also using the same inference using MCM sampling method, MCMC, samples posterior distribution of attack defense values and determines the most likely team strengths. And this model learns attack defense strengths that best explain past match scores. Because it's very simple, this very simple parameters to use for this model. It's only like using global, so there are less variation to worry about with the small data set. So let's talk about the hyperparameters of this model. These parameters define general trends across all teams, and this is the baseline goal scoring formula, the hyperparameters, which is using global normal distribution. And home advantage is optional, but it's added here because you want this single level model has a little bit more condition to analyze the team strengths. So the team specific parameters for each team, we just assigning another fixed normal distribution. And then this model will continue to do the score modeling and by adding up using the formula. And these priorities not necessarily prevent extreme values, and everything is centered to 0, and it's not really sometimes a small data set will have another means of least average, which the average score across the league data set. Sometimes this would be very unrealistic because the model is not shifting while we capture more data. And then we later will have something that fix these issues. And let's continue the next slide. Score rate modeling. We use this lambda and with the explanation, which explanation of the home score and away score with the base global normal distribution and for both home and away team here. So next will be and we're using explanation for this model because Poisson distribution requires a positive go rate. Well, that's a very straightforward answer. And this model also able to capture the randomness in goal scoring. And we're using the likelihood function. And the model has faster computation and easier to train. That's because it requires fewer parameters since each team's attack defense string is estimated independently. It does not involve league-wide power areas that require additional sampling. And on the other hand, multi-level is slower on this smaller data set because it has small parameters, more computation powers to use to span on. And also it has to capture the league-wide match data while they are computing the team-specific data. And for the interpretability of this single-level model, it's like teams' attack and defense values are directly linked to goals. And you can represent by the simple relationship with the formula. Let's see. So it works well with enough data per team. If a team has played many matches in a small data set, it will be accurate and no need to using the multi-level pooling to train the data, to train the model, to let the model learn from the data set. The cons about this single level model could be overfitting easily, and because extreme failure could happen because small data set means there will be uneven portion of team match records. Let's say some team, maybe one team in the data set will have 100 or 50 matches, and at the other hand, many teams and in this data set only have like 2 or 3 or maximum to 10 matches in this data set, which causes the extreme values on normal distribution and causing overfitting, because that means the model is not learning anything from the data set because this data is not, team data is not enough. So it means two not enough data for the specific team that causes the model not able to learn from the team strengths. Um, like I said, it has no borrowing of strength. Um, there's no information is shared between teams. Each team's attack defense is learned independently. If a team has played only two to three matches, the model has no way to correct extreme values. Poison model gives fixed attack defense values. It assigns a single attack and defense value per team, does not account for uncertainty. Doesn't look like middle-level models account for. However, doesn't borrow the power of attack and defense from the other team to get the estimate for the small team. Doesn't borrow that probability for that. And the prediction from Poisson regression are overconfident. And Poisson model assumes we are 100% sure about a team strengths, which it gives precise match score predictions even when there is very little data. In reality, match outcomes should have more uncertainty. So what I did to modify this model in make it match to the multi-level model, the result of multi-level model is to make it more marginalized, which means make the distribution is more marginal for each team, and apply the offset just like the multi-level does to normalize the goal scoring formula. Um, and that way, we're just preventing the extreme estimate from the single level model, while to achieve the similar uh, probability outcomes, just like the middle level model does, while spend way less time to get the computation out result. Uh, less time, spend less time on the computation. So here's what I found from multi-level. This is the normal distribution for the single level model, the Poisson regression model. This is the attack power for both teams. I specifically choose these two, just like the last mini project does. Defense power and defense from both teams are pretty similar to what we found from there. The multi-level model team and the single-level model team has a very similar result here. And the heat map, as you can see, there's very similar performance, and we found out it has way less computing time that's spent on the single level model. From my experience of the multi-level model, it spends at least 15 to 20 minutes on that 300 entries on that with that small data set. While this single level model to achieve very similar result using only 5 minutes, around 5 minutes, and to get the uh, very similar result from there. So thanks for watching. So I'm the project contributor, and here's my the video link will be provided as soon as I finish this recording. Thank you.